Alright, AP Chem, here is your video lecture for Chapter 6, Section 3. We're going to talk about Hess's Law. So, when dealing with changes in enthalpy, calculating the change in enthalpy, whenever you're going from a particular set of reactants and you're trying to end with a particular set of products, the change in enthalpy, that value, is always the same regardless whether or not the reaction takes place in one step or it takes place in a series of steps. There could be a reaction that has 5 steps. It's going to have a certain change in enthalpy. As long as those first reactants are the same and those end products are the same, it doesn't matter if that reaction happens in 1 step or 5. The total change in enthalpy will be the same. And so the sum of those 5 steps, the change in enthalpy of each of those 5 steps will add up. They will sum to be the change in enthalpy of the reaction that takes place in one large step. And that's basically the idea behind Hess's Law. And this section we're going to talk about how to use that idea to calculate changes in enthalpy, that delta H. So here's an example. We have the reaction nitrogen gas N2 plus O2 oxygen gas reacts to yield nitrogen dioxide. Now this reaction does not happen in just one fell swoop. You do not mix together nitrogen and oxygen and in one reaction get nitrogen dioxide. There are actually 2 steps. There's an intermediate step. First off, nitrogen gas is going to react with oxygen gas and react to form nitrogen monoxide. Now that nitrogen monoxide that was just produced will go on to react with oxygen gas also. And as the result of that reaction, we get nitrogen dioxide. So this reaction actually takes 2 steps. Now notice that each of those steps has a certain change in enthalpy, a certain delta H. Delta H after the first step is 180 kilojoules. Delta H after the second step is negative 112 kilojoules. All right. Now, we have indicated up here at the top, let's see, delta H1, just representing this overall reaction. This is an overall reaction. The delta H of this overall reaction is 68 kilojoules. But notice that the delta H of the first step summed with the delta H from the second step equals 68 kilojoules, the same as this delta H1. That's all I wanted to point out, that delta H1 here is equal to delta H2 and delta H3 added together. And that's Hess's Law. When we go to actually take the intermediate steps and, I have one more, and generate the overall reaction, okay, let me take this off. Notice that there's an intermediate step that involves NO as a reactant, or not as a reactant, as a product. But in this overall reaction up at the top, there is no NO, there is no nitrogen monoxide. That's not represented in the overall reaction. That's because as an intermediate, okay, this nitrogen monoxide is produced and then is turned around and it is utilized in the next reaction. So it's produced, but then it's used up. Okay, it's an intermediate step. It's not represented in the overall because there's no nitrogen monoxide left over. Okay, at the end of the day, there's no nitrogen monoxide left over. And so what we do when we go to generate the overall reaction, okay, the oxygen plus nitrogen equals nitrogen dioxide, that overall reaction, we are simply going to cancel out any species that are represented on both reactant and product side of the reaction arrow. Now in this situation we have 2 NO as a reactant and then 2 NO as a product. We're simply going to cancel those out. And once we've done that, we've canceled out everything that needs to be canceled out, or can be canceled out, I should say. After we're done, we're going to have 1 N2. Notice that we have 2 O2s right here. So we have 1 N2 and then 2 O2s react to yield 2 NO2s. All right. So we're going to be using this exact same procedure to carry out, to calculate the answers that we need for this section. Here's a graphical representation of the principle behind Hess's law. If we have a two-step reaction, okay, using the same example, oxygen and nitrogen reacting to form nitrogen dioxide, the overall reaction produces, I'm sorry, I got messed up here. Delta H2 has a value of 180 kilojoules. Delta H3, like we said before, it has a value of negative 112 kilojoules. So in order to generate this unknown, here it's red, this delta H that's unknown, we simply find the difference between 180 kilojoules and negative 112 kilojoules. The difference there. Okay, so we have the enthalpy H increasing, going up 180 kilojoules. But then the second step of the reaction, we have delta H going down. Delta H going down 112 kilojoules. And so in order to find this leftover, it's simply the difference between 180 kilojoules and negative 112 kilojoules. And simple subtraction will let us in, will tell us that it's 68 kilojoules. Okay. So characteristics of enthalpy change. If a reaction is reversed, okay, in the first example we have nitrogen gas plus oxygen gas reacts to yield nitrogen dioxide. It has a delta H of 68 kilojoules. If we were to reverse that reaction, so we would have nitrogen dioxide decomposing into nitrogen gas and oxygen gas, we would simply reverse the sign of delta H, and that's it. We'd have negative 68 kilojoules. Second thing to remember, the magnitude of delta H, okay, in that example it's 68 kilojoules, the magnitude of delta H is directly proportional to the quantities of reactants and products in a reaction. If the coefficients of a balanced reaction are multiplied by an integer, the value of delta H is multiplied by that same integer. So, as we'll discuss in this next example, if I have to multiply all of the coefficients in a particular reaction by 2, okay, in order to get the math to work out, I am going to multiply my delta H, which in that example is 68 kilojoules. I'm going to multiply that by 2, so I'll have 136 kilojoules. All right, so here's the example we're going to work with. So considering this data, this is the information we have. Okay, we have ammonia gas decomposes into nitrogen gas and hydrogen gas, and we have a delta H of 46 kilojoules. We also have the information that hydrogen reacts with oxygen to produce water, and that reaction with these molar coefficients has a delta H of negative 484 kilojoules. That's the information you have to work with, and you will be given this kind of information when you're asked to complete these sorts of problems. So given this information, you are to calculate the delta H for the reaction. Now, in general, these are the steps that you're going to take, and in general, these are the only steps you're going to take. There's not going to be a whole bunch of left and right thinking. It's just this is your strategy. This is the system that you are going to remember when working these problems. Okay. first off, you're going to work backward from the required reaction. Okay, I want to point out again, calculate delta H for the reaction. Nitrogen and water react to form oxygen and ammonia. You're going to work backward from the required reaction. Okay, using the reactants and products to decide how to manipulate the other given reactions that you've been given. Okay, up top, the two equations that are given up top are the things that you're going to manipulate in order to get the information that you need. So after you've done that with that idea in mind, you're going to reverse any reactions. Okay, those two reactions up top. You're going to reverse any reactions as needed to give the required reactants and products. Okay, once you've done that, we'll simply multiply the reactants to give the correct numbers of reactants and products. We'll mess with the coefficients. All right, so here's our situation. The desired reaction is down on the bottom, and I want to point out that what we've done here is we've actually flipped both of the given equations up here at the top. Go back a few slides. We have ammonia decomposing, and then we have hydrogen gas and oxygen gas synthesizing, but we've flipped both of those reactions. We've flipped both of those reactions because for our desired reaction, the thing that we're trying to work towards, we have nitrogen gas and water on the reactant side, and we have oxygen and ammonia on the product side. So back to where we started, our reactions are flipped. So we're going to flip that again, but we're going to flip these reactions, but we also have to change the sign of delta H. Okay, these delta H values, we're about to flip these bad boys so that we have hydrogen, or so that we can get nitrogen on the reactant side. We're going to flip this one as well so we can get water on the reactant side, but because we're going to do that, we're going to need to change the signs of these delta H values. All right, so we've done that. We've flipped the equations so that nitrogen is on the reactant side. We had to bring hydrogen with it, of course, and now ammonia is on the product side. We've also changed the sign of that delta H. It is now negative 46 kilojoules, and we have water on the reactant side, which is where we want it for our desired reaction. Okay, we can see that right here. And then we have oxygen on the product side as well, and we had to bring hydrogen along for the ride. But notice that the delta H is now positive. We've flipped that. All right, now that we've flipped those equations and we've changed the delta H as we need, we're now going to multiply the reactions. Okay, multiply the entire reaction, all of the coefficients in the reaction, by a certain number, and it's not always going to be the same number, in order to get the correct number of reactants and products. So I want to have two N2 molecules. I want to have two nitrogen gas molecules, and so with the given equation, I have half nitrogen gas molecule, so I'm going to multiply everything in that equation by 4. So I'm going to end up multiplying the 1/2 by 4, I'm going to multiply the 3/2 by 4, and I'm going to multiply the 1, that is the coefficient for ammonia, by 4. And don't forget, I'm also going to multiply the delta H, the change in enthalpy, by 4. Because remember, that was one of the things I pointed out earlier. You have to, the delta H, the change in enthalpy, is directly proportional to the quantities of the reactants and products. So multiply everything there by 4. Next given, I want to have 6 waters. Okay, and my desired reaction, the thing I'm moving towards, I want to have 6 waters. So I have 2 waters in the equation given. I'm simply going to multiply everything by 3. Okay, everything by 3. The coefficient for water, the coefficient for hydrogen gas, and the coefficient for oxygen gas, as well as delta H for this equation. I'm going to multiply them all by 3. Now, once I've done that, I'm going to have the two equations, 2 N2 gas plus 6 H2 gas reacts to yield 4 NH3 gas. And there's going to be a total delta H there of negative 184 kilojoules. My second equation, I'll have 6 waters, okay, 6 water vapors, decomposing into 6 hydrogen gas and 3 oxygen gas with a total delta H of positive 1,452 kilojoules. Right, I'm not done quite yet because if you've noticed, I have some hydrogen gas in these two equations, and I do not want them in here. But luckily, notice there's 6 hydrogen gas on the reactant side, and there's 6 hydrogen gas on the product side, and they simply will cancel each other out. They're going to be intermediates, and they're going to be used up, and they will not be present in the product as one of the products, and they do not need to be present in the reactant. So now I have what I've accomplished. What I've accomplished is I have 2 delta H values that I will now sum. I will now add these together, and they will generate the value of 1,268 kilojoules, which is the answer that you are going to submit. You'd square that out on your test, on your quiz, or on your worksheet. So you've calculated the delta H for the desired reaction now. And that's the entire section 3 right there, is using Hess's Law. You're going to use this same system no matter what problem I give you. There may be a little change in the way you go about that, but in general, you're going to copy this exact system every time you carry out one of these calculations. Again, if you have an issue, be sure you are reading the book. There are good sample problems in there for you to try. Be sure you're completing your assigned worksheets, and if you're really desperate, send me an email, or a quick Google search or a search on YouTube can be very helpful. If you do have an issue that you can't rectify on your own, be sure to come to class with that question and ready to work. All right, I will see you next period.